Okay, I'd like to thank everyone for joining the EMA webinar series. The topic today is Galileo EME, Advanced Simulation Platform for RCS and IR Simulation. This is Tim McDonald, Chief Scientist of EMA. EMA is in Denver, Colorado. EMA is the distributor and support representative for Galileo EME in the United States. Speaking today, we're very happy to have Raffaele Scuderi. Raffaele received a master's degree in telecommunication engineering from the University of Pisa in 2010. Then he joined the microwave and radiation laboratory at the University of Pisa and has been a visiting scholar at the EM lab at Penn State in the US. And in March 2012, Raffaele joined IDS and is currently charged with product management and development of IDS's software products for electromagnetic simulation. So thank you very much, Raffaele, and I'll turn it over to you.
Yes, thank you very much, Tim, and thank you, everybody, for attending this webinar on Galileo EME. Like Tim mentioned, Galileo EME is a software tool for the electromagnetic simulation of large and complex platforms. This software tool is focused on the signature from the point of view of the radar signature and infrared signature. Galileo EME has been designed as a helpful tool for system engineers and all those people that are involved in long-term assets activities, consulting services, staff program, platform design program, midlife refitting activities, and all those activities that need to manage several data, a really huge amount of data that can be generated and analyzed in a quite long-term activity. Galileo EME is not a typical commercial off-the-shelf tool, but is a tool that IDS has developed at the beginning for carrying out our consulting services and our own activities. So it's a software tool that is based on what we call our 3 pillars. So capability of simulations, capability of consulting services, and measurements that IDS usually carry out for its customers. In Galileo EME, system engineer, an electromagnetic engineer will find several capabilities that can be useful during his typical activity. In this regard, with Galileo EME, we can create several projects. For each project, we can have several versions. Each version can contain a main CAD model that usually follows the configuration of the platform, but for that configuration, we can analyze several times and with different software tools that model. So we can compute several mesh models and we can analyze those mesh models several times with different software tools and with different solvers. When I say different solvers, I'm talking about asymptotic solvers or full-wave solvers. In the same way, also the infrared section will follow this procedure. During this presentation, we are going to focus just on the RCS section. This is the graphical user interface of this software tool. As you can see here, we have 3 main windows. On the left, we have the navigation tree. In the middle, you can see a navigation panel. And on the third window on the right, we have an additional window wherein we can generate and visualize some useful data. The meaning of the benefit of this third window is that when I have generated a lot of data, sometimes it could be difficult to recognize and retrieve that data. So for this reason, maybe instead of just a name, I need something else for recognizing this data. And in this regard, I can say, for example, some picture of a mesh model or some picture of specific results that can help me in recognizing this data. Moreover, since after a certain period, those data can be really a huge amount, I need some capabilities also for grouping or filtering out some data. All these tools are for simplifying the life of the application engineer. When I select a mesh model, so a single row in the navigation panel, immediately the ribbon bar will be customized based on the data that I have selected, like depicted in this slide. And this is for guiding the user, for helping the user in the usage of the software. Galileo EME includes several solvers, several electromagnetic solvers, but on the other hand, it includes also a geometrical tool for generating the geometrical model I have to analyze, and also for meshing it. The mesh can be different based on the different solver that I want to use. Let's have a look of the typical analysis type that I can run with Galileo EME. I can run monostatic and bistatic RCS and imaging as well. Hourglass plot, inverse synthetic aperture radar analysis, moving target simulating the trajectory of a target, jet engine modulation, structure currents, and hotspot for diagnostics. As I mentioned, when I select a row in the software tool, I can then exploit the ribbon bar for scheduling the analysis. And when I do that, I need to specify all the typical parameters of this analysis, such as frequency and settings of the specific electromagnetic method I want to use, scan details, and I'm talking about aspect angles. Finally, when the simulation is completed, Galileo EME provides the user with some basic and also advanced post-processing tool for a better visualization and an immediate visualization of the results and comprehension of the results. As I mentioned, Galileo EME is a multi-method software tool. We have the two families, full wave software solver and asymptotic solver. In the full wave family, we have the standard MOM, the synthetic function expansion, the multi-level fast multiple method for the frequency domain method. For the time domain method, we have the finite difference time domain solver, 3-dimensional and 2-dimensional. We also have a periodic method of moments that is suitable, for example, for analyzing periodic structures like frequency selective surfaces and so on. In the family of the asymptotic methods, Galileo EME provides the physical optics, including the diffraction of perfectly conductor materials and also dielectric materials, and the shooting and bouncing rays. All these solvers, all these analyses can be considered in a multi-method approach. So finally, when the simulation is finished, the overall results, it could be contributed by several different solvers. For example, if I have a quite complex and large platform, usually if we suppose that I have to analyze an aircraft, for the fuselage of the aircraft, maybe an asymptotic method could give me a quite accurate result. This is not true for some specific details of the aircraft, like, for example, antennas or cavity. In that case, I can compute the RCS of different parts of the target, and then I can combine finally all the results that comes from all those parts of the aircraft in one overall result. And this is our multi-method approach. In Galileo EME, we also exploit the monobistatic theorem. The monobistatic theorem is quite useful for the iterative methods like a multi-level fast multiple method or finite difference time domain. Thanks to the monobistatic theorem, we can speed up the simulation. Another distinctive feature of Galileo EME is what we call decoupling procedure. The decoupling procedure is suitable for computing the RCS that comes from the internal part of a general cavity, like an intake, or in general, every cavity can be treated in this way. For example, if we suppose that the aircraft in the picture is our target, and I want to analyze the external fuselage of this aircraft with an asymptotic method. In that case, I need to create 3 different mesh models. One mesh model for the external part of the fuselage, another mesh model for the intake, and the third mesh model for the outlet of this aircraft. In this case, if I simulate just the intake in a freestanding configuration, for sure I will make a mistake when I consider the RCS of this target. And the reason is that I'm including in the result also the contribution that comes from the external part of that cavity. And as is shown in the picture in this slide, sometimes this mistake can be really big. So for this reason, when we analyze this kind of target, we define a mouth in the mouth of the cavity that is some kind of decoupling surface. And then we get just the scattered field that comes from this decoupling surface. In this way, we can take into account the masking effect of the fuselage of the aircraft on the intake. The Galileo EME RCS section has the capability of computing the RCS and also radar image, but also we have capability of diagnostic. Because whenever we get some weird contributions, some weird peak in the RCS plot, then we have capability to investigate the reason of this contribution, and we can also try to reduce, we can try to treat this specific part of the platform based on the information that we get from these diagnostic tools. That could be a radar image, or also some specific simulation that we call hotspot. The hotspot is a 3D representation of the RCS that is coming from some specific part of the mesh model. The structure current is another diagnostic tool as well that could be useful for understanding what's going on my target. RCS of antennas. RCS of antennas is another very specific problem, still complex for electromagnetic engineers, because as we know, the RCS of an antenna is basically due to 2 different phenomena: the structural mode and the electrical mode, antenna mode. With Galileo EME, we have capability to model with a absolutely high fidelity the geometry of the antenna, and this is good for the structural mode. but on the other hand, we also need to model the termination on this antenna. And for this reason, we can consider also some load condition on the antennas. And we have also a dedicated procedure for managing really huge arrays of antennas. Another distinctive feature is the capability of including a contribution that comes from gaps. This kind of contribution is typical of a full-wave method, but in Galileo EME, we have a specific library that allows the user to define some canonical gaps, and modeling the behavior of this kind of gaps, we can include this contribution when we carry out the simulation of the target with an asymptotic method. In this case, especially with the physical optics. So we can consider this kind of full wave contribution also with an asymptotic method like the physical optics. These gaps can be a canonical shaped gap, or it could be also some custom shaped gap. And in this case, we can compute the behavior of this gap carrying out a two-dimensional FDTD simulation. Jet engine modulation. The jet engine modulation is quite useful for people that are involved in not cooperative target recognizing. Thanks to the jet engine modulation and also to other additional parameters, all those people can detect the typical fingerprint of some specific target. And this is true, and it is applicable for rotating part of the aircraft, like engine or blades in general. In Galileo EME, we can analyze huge platform with asymptotic solvers, but we are also, right now, we reached a quite good level for analyzing quite big size target also with a full wave method. In this case, I have shown structure current computed with our multi-level fast multiple method, and I think that this target has a size that could be quite impressive for a full wave method. It's something like 760 lambda. Here we have a list of other additional capabilities of Galileo EME. We can take into account the effect of the multipath, for example, for ships on the sea. All the solvers are fully parallelized. We can compute and exploit frequency selective surfaces behavior. We can consider several roll and pitch for the attitude of the target. All the data consistency is kept thanks to the Oracle database that is the engine of Galileo EME. And one distinctive feature of Galileo EME is that we do not compute just the RCS itself, but we also can consider some advanced parameters like detection probability, detection range, range advance factor, and self-screening range. The typical hardware and software configuration of Galileo EME could be from just a simple standalone machine going through a complex client server and slave configuration. This is scalable and allows the user to exploit all the computational resources and power that they have. So I would like to immediately go to the live demo here. So I will open the software. As I mentioned, Galileo EME is a multi-user software, so several people can access to the same data. So let's suppose that we are a team of people, then we can have access to the same project, for example. And for this reason, I have to log myself. This is the user interface, and here you can see all the users, for example, for this specific installation, and all the projects that I have. Let's create immediately a new project, demo project, here, and now I'm inside the project. Let's create immediately a new mesh model. It's new. Let's see how to create and analyze a corner. So this is our geometrical tool here, and I create the mesh model of a corner here. This is the geometrical model, and then I have to compute the mesh. Here you can see the mesh that I have computed. I can align the normal in this case, and the model is done. Just close and save, validate the model, and you will see here that the model is here. Then, for example, if I want, I can also have a preview of this model, and I can save a picture of this model that maybe will help me in the future to recognize this specific mesh. So save by selection, for example, selection, apply, and I can save here a screenshot of the model that will be available here on the third window. And I can use this picture, for example, for putting it in my report, in my document, for showing it to my boss, and so on. When I select this mesh model, immediately the ribbon bar will be customized based on this specific model. This is a model generated for an asymptotic method. So here I can use the physical optics or the shooting and bouncing rays. If I push physical optics, immediately I will get all the parameters of this solver. In this case, I'm choosing a reflection order 2, frequency 10 gigahertz, and scan details from 0 to 90, and also in elevation from -10 to 10 with step 5, submit. As I mentioned, the tool is parallelized, so I can split this simulation in several runs. In this case, I'm not going to do that. And I have scheduled the simulation. All the simulation are managed here with this procedure manager. And I can decide to run this simulation here, and I can check when the simulation is finished. Here you can see the percentage of computation of this simulation, and when the simulation will be finished, the results will be available here behind this node here, analysis RCS. I can immediately select this node and pushing view result. Of course, I will get a map. that could be just a two-dimensional visualization or three-dimensional visualization. I can change color, whatever I like for this model. I can also move it if I want. I can change the representation mode. And finally, if I need it, I can also save this result, RCS Map. And the result will be available here on the third window. So all these features are conceived for helping people to retrieve all the data that maybe they will create during their project, during their activity. So that was just for giving you a very brief feeling on how to create a model, generate a model, and analyze it. Of course, with Galileo, now I have created just a PC corner, but with Galileo EME, we can manage several kind of materials, like a simple dielectric slab, where I can put the epsilon and mu constant. And what is nice of this tool, in my opinion, is that I can immediately analyze the behavior of this material here in terms of reflection and transmission, also coefficient that you can see here. And I can do that as function of the frequency, but also as function of the angle. In this case, I can analyze the material around here, 16 gigahertz. And you can see the reflection coefficient as function of the aspect angle. This is the model of a quite simple dielectric slab, but we can also model a multi-layer, so multi-slab model. I can define several layers and so on. For example, this is quite typical for designing a radar-absorbing material and analyzing immediately the performance of this material. Then we can create all this material and we can install this material in our mesh models. So then let's go straight to a typical complex platform, like it could be an aircraft. Usually, when you deal with a complex platform, usually you don't draw your model by your own, but you get the CAD model maybe from some manufacturing company. And typically, this CAD model is a quite good mechanical model, but typically, at least in my experience, is not that good for the point of view of the electromagnetic simulations. And the reason could be different. You could have several reasons for making it a nightmare for the electromagnetic engineer. Here in this model, I have imported CAD of an aircraft that shows some of the typical problems that I can get in this model. And for example, here I got a hole. This hole in reality is not in the aircraft, but maybe for some reason is in the CAD model that I got. How can I fix this problem? Our geometrical tool provides the user with some dedicated tools for managing these kind of problems. For example, I can immediately close this model by boundary, and the hole is not in the model anymore, is closed. Here we have three levels of representation. We have the geometry, that are the mathematical surfaces that are describing my model, and we also have the topology. So when we have the topology, it means that we have all the connections between all the patches, and all the connection that I realize here in the geometry will be constraints for the mesh model. In this case, for example, I have two different edges that are very close to each other, but still two. This kind of problem will lead to some mistake or not that accurate simulation, for example, for a MOM solver. And I can decide to fuse, to merge these two edges here. So just going on with this procedure, finally I will fix all the problems that I potentially have in my target. And then the target will be ready to be meshed for an electromagnetic solver. In this case, I have already done this cleaning stage. The cleaning stage, in our opinion, in our typical workflow, is a quite important and sometimes also long activity when we start with a new project. So let's have a look of the mesh model that I have computed for this aircraft, the Sea Harrier, and this is a mesh model for an asymptotic method. Here, for example, the model is basically made by PC, but for example, the canopy is made by a polycarbonate material, is the dielectric slab. The radome is dielectric as well. And the cavities here are made by PC. So I run the first RCS simulation for this target. This is the baseline configuration with, for example, with the SBR. And I got here this plot. So let's suppose that that was the baseline configuration and that I need to reduce the RCS of this aircraft. I can immediately see that here I have some peaks, and also here it seems something like typical corner effect, but honestly it's not that clear what kind of phenomenon is generating, for example, this corner here. So how can I know something more about my target? I can try to compute what we call an hotspot analysis. So just fixing the aspect angle here and just pushing. In this case, I want to take into account up to the third order reflection for the simulation, and I can do also that in real time for you. And the result of this simulation will give me some indication on the main scatterers that are contributing to the overall RCS here. And I can have a two-dimensional representation or also a three-dimensional representation, like here. And here, for example, you can see that seems that here and here I have some hot spots. But since I'm using a ray tracing method, I can also check who is the phenomenon that is generating these hot spots here. As you can see here, I got a first order reflection from the fin of the aircraft, but also if I'm interested on the second order phenomenon, I can see that I have a first reflection here on the back part of the missile, and then the second order on the fin. So a quite simple conclusion could be installing some radar absorbing material here on the fin of the aircraft. And that's exactly what I did here in the low observability model. Let's have a look of the benefits that I got in the RCS in the overall RCS installing some radar absorbing material on the fin, and actually I have also installed some radar absorbing material inside the cavity of the aircraft. So let's compare the performance of the baseline configuration and low observability configuration. Let's cut here for a constant elevation, and you can see here that I got a reduction of the RCS because I've installed a radar absorbing material on the fin, and also here in front of, on the nose of the aircraft, because I have installed some radar absorbing materials inside the cavities. So that was an application example of the usage of asymptotic solvers for a complex platform. I would like to show you also how to face a complex platform exploiting a multi-method approach, and I'm gonna do that considering this target here. The target in this case is a UAV, and the UAV here shows some specific feature that will help me talking about our multi-method approach. As you can see here, this target has a quite flat fuselage and also an inlet inside and an outlet here. My approach in this case is gonna be simulate the external fuselage of the aircraft with an asymptotic method, and the inlet and the outlet that are complex shaped structures, and sometimes also with some radar absorbing materials installed inside, and then combine all those results for computing the overall contribution. And the inlet and the outlet will be simulated with a full wave method. So for this reason, I have generated 3 different models. One model for the asymptotic solvers and 2 different models for the inlet and one for the outlet. So in this case, there could be also several configurations. Let's suppose that I have the inlet, in this case, that is made by TC. Like I mentioned, in this case, it's better if we use the decoupling procedure approach, because when I simulate these targets, I don't want the external contribution of the cavity. So for this reason, I have generated the mesh of the inlet that is here, and also the mesh of this mouth here. Just defining this model and setting here in this internal volume with the flag cavity, the solver will neglect all the external contribution from the cavity and will consider just the backscattered field from this mouth. In the same way, I have generated the mesh model for the outlet here. And I also, in this case, I have closed the outlet hole with the mouth here, and then I set the cavity flag inside this structure. For the external fuselage, I have computed an asymptotic mesh model, and according to the same principle like for cavities, I need to remove the external contribution of those structures. For the fuselage with cavities, I need to remove the contribution that comes from this part here. And for this reason, I have installed here in the interface of the inlet a perfect absorbing material. So I don't get any RCS from the inlet interface and from the outlet interface, but I get just the scattered field from the fuselage of the aircraft. Then I have simulated all these structures here, and I have done that at 6 gigahertz. For example, you can see that now I have quite a big amount of data, so it's not that easy for me retrieving this data, but I know that I carried out this simulation at 6 gigahertz, so I can just filter by frequency. So I can consider this result here and also the SBR that I have computed, and I can define a collector. In this collector, I put the PO analysis for the fuselage, the multi-level fast multiple method simulation for the outlet and for the inlet. And let's see how I can do that. So I can put here all this contribution, and I can select which contribution I want from each one of the simulation that I'm considering. For example, for PO, I can consider the first order and also the diffraction from edge or wedge, and eventually the contribution from gaps or cracks. For a full wave method, of course, I will consider just the full wave contribution. And finally, I can save the final result like total contribution. Compute and save. And now I can get this result like another one. So if I finally select all this simulation here, we can check here all the results that I got. Okay, and here you can see that the total result is the black curve. The external part of the fuselage is the blue one. The red one is the contribution from the outlet. I can also make the overall dashed. And the blue sky color is the contribution from the inlet. Here you can see that the RCS is dominated by the inlet. Here we can clearly see the leading edge of the UAV, and also here. On the back part of the aircraft, the RCS is dominated by the red curve, so the outlet contribution. We talked about how to schedule an asymptotic solver simulation. Let's have a look also on the simulation that I scheduled, for example, for the inlet or for the outlet in this case. As you can see here, immediately when I select an analysis, the ribbon bar allows me to run another one. And run another one means inherit the previous one, because I can immediately, just pushing here, choosing the right solver, I get all the settings already set for me. So the mesh model is this one. The analysis settings are already set for me. So double precision, the number of cores that I want to use. In Galileo EME, for the MOM-based solvers, we have the electric field integral equation and combined field integral equation as well. We have the capability of treating dielectric materials with a surface impedance approach, exploiting the impedance boundary condition approach, or we also have the Poggion-Miller, Chang-Arrington-Woodside formulation that allows us to model a real high-fidelity three-dimensional model. For a multi-level fast multiple methods, there are all the typical settings. Here, the tolerance of the iterative method, near matrix extension. Since it is a iterative method, if we start from a well-conditioned problem, the simulation is going to be faster, so we have some preconditioner. And also we can choose the solution method for this simulation. All these parameters must be tuned based on the specific target that I'm analyzing. So that was an example, an application example of the application of multi-method approach and also of the decoupling procedure. I also would like to spend a couple of words on the decoupling procedure, just showing you an example of quite complex cavity that will highlight the capability of the solver, but also on the other hand, the capability of the geometrical tool and meshing tool. The cavity that I'm showing you is a quite complex cavity with quite a lot of triangles here. Here you can see some details of the cavity, and also consider that I'm performing this live demo on a laptop. So here, for example, I can remove the mouth, and you can appreciate the details inside this cavity. And this target has been simulated also with the decoupling procedure, so completely neglecting the external part of the cavity and just defining this decoupling surface here. Okay, so I think the time that I have is pretty much finished. So if there are any question, I think is the right time for giving you the chance to ask some question. Yeah.
Thank you very much. That was fantastic. So we have a couple questions. So in your practice of doing consulting, what are the practical impacts of having the use of full wave methods in addition to only asymptotic methods?
Yeah. So usually, especially when we analyze quite huge, for example, naval ships, an asymptotic methods is quite good enough and quite good accurate. But especially for aeronautical platforms, usually a full wave method is the only way that we have to reach very high fidelity, very accurate results. For example, here I can show you some results and some performance of our multi-level fast multiple method solver on some aeronautical targets. There are some phenomena that are quite typical also of aircraft and this kind of structure, like traveling waves, creeping wave, and the only chance that we have is exploiting a full wave method. Also for cavities, especially for ram-treated cavities, complex shaped cavities. Also in that case, in our experience, we have seen that only with a full wave method we can reach a very high fidelity result, very accurate results that we can compare with measurements, because we always, when we do our consulting services, we tune the mesh models several times, and also simulation will be helpful for tuning measurements in the loop of the three pillars. And so only with a full wave method we can think to compare, to have a fair comparison between simulations and measurements. Usually asymptotic methods are quite good, but in that case the user must be the driver. If we give a mesh model to the full wave engine, in that case we will get always the best result. Of course, it's time consuming and physical memory consuming, but it's the only way that we have to reach a very high fidelity, very accurate result.
Thank you. Another question we have, as you know, there's many general full wave packages on the market commercially. What do you think as a practical user of software in a consulting practice, what's the difference between this platform that's dedicated to RCS and a platform that's a general solver?
Yeah, I mean, my personal opinion and what we have seen, what we see every day in our typical job is that with a typical commercial off-the-shelf tool, we cannot solve our own problems. Especially for our consulting services, we do not have the right answer or the answer that we need from a commercial off-the-shelf tool. For this reason, IDS in the past has decided to develop our own solver, our own framework, our own software tool. Consider that this Galileo EME is not conceived to be like a commercial tool. The beginning of this software tool is create a software tool for myself, create a software tool that will solve my personal problems. And finally, we have seen that that software tool has been appreciated also by our customers that are involved in pretty much the same activities in which we are involved.
Thank you very much, Raffaele. With that, we're going to wrap up this seminar. Again, if you have questions about these tools for United States customers, you can contact us at EMA. We're at ema3d.com. I'm Tim, T-I-M, at ema3d.com, and I can pass along any questions you have to Raffaele and the other members of the team. Thanks a lot for your time in joining this seminar. We will be following up with a recording of this webinar, as well as more information if you need more information about this tool. Thank you very much.
Thank you very much, everybody.